For anyone that's taken geometry, algebra 2, etc., you probably remember this special triangle. Today we're going to derive it, but we're going to use radians because degrees are kind of arbitrary. So let's think about this in radians. There's 2 videos I've done in the past, so watch those to understand how we get this. So the sum of the interior angles of a triangle are pi radians, and then half a circle is pi radians. These are our fundamentals we have to know. If you don't know these fundamentals, watch my videos. I'm going to link them in the description. The second fundamental you need to know is what an equilateral triangle is. An equilateral triangle, all 3 sides are equal. So this side is equal to this side is equal to this side. The other property of an equilateral triangle is the interior angles, each one of them, are equal to each other. So we have to know this property of a triangle. Now that we know this property of a triangle, since the 3 angles are equal in there, and we know the sum of them is pi radians, we can derive what each angle is, pi over 3. So I wrote it another way. If you add the 3 angles up, it equals pi, but this divided by 3 equals pi over 3. So this is each individual angle inside an equilateral triangle. It's pi over 3. Next step, if we took this equilateral triangle and then bisected, aka split evenly down one of the angles. So now there's an equal angle here and an equal angle here. So I wrote that by pi over 3 divided by 2, which equals pi over 6. We would get this shape. And because I split it evenly down the angle, I also bisected this base right here. This length is equal to this length. So if we just took this side of what we created, we have a pi over 2, again, because half a circle is pi radians, so a quarter of it is pi over 2. We have a pi over 2, we have a pi over 6, we have a pi over 3. Since we know it's an equilateral triangle, we can give the lengths some length. So let's give the lengths all a 2. So let's say each side of the triangle is equal to 2. If we're just going to look at this triangle here, since we split the base in half, now it's a 1. This side is still a 2. And we also know that this is a pi over 2, which means it's a right triangle. So we have a special right triangle. And in fact, we can just do the Pythagorean theorem. C squared, which is 2 squared, which is 4, equals b squared plus a squared. 1 squared is 1. So we subtract the 1 over, and b is the square root of 3. So there we go. We just derived this without degrees. Now, obviously, you can just divide everything by 2. You would get what this would look like on a unit circle. If you guys remember a unit circle supposes that the radius is 1. So we're making a circle with a radius 1. We can just derive this again if we wanted to go back to the method I showed you. So this time we're going to use the length of each side is 1. And we remember that the angles inside is pi over 3. But since we're dividing that evenly, so now each side is pi over 6. So again, we have a pi over 3, a pi over 6, a pi over 2. Since we divided this one evenly, now the base is a half. The longest side is 1. So again, we use the Pythagorean theorem. C squared, 1 squared is 1. And then a squared is 1/2 squared, which is 1/4. And then we subtract it over. 4 over 4 minus 1 over 4 is 3 over 4. And then we get the square root of that. And so that's root 3 over 2. So in a unit circle, we have 1 root 3 over 2 and a half. So when we learned trigonometry, we learned to convert from degrees to radians. But what we can see is we can just think in radians. We don't need to think in degrees. And in fact, it's much more helpful just to think in radians and build it. So when you go into calc, go into multivariable calc, etc., you don't need to have degrees stuck in your head anymore. Radian calculations are much better and much easier, much more efficient when you get to the higher maths. So this is an example from one of those pesky 1-2-3 ratio right triangle identities that we had to remember. Now, even if you don't remember it, you can derive it yourself using radians. Thank you guys so much.